All right, welcome to Math 331, Problem Solving, Lecture 29, Take 3. Seeing if we're having some technical issues today. All right, so this is going to be the third time attempting to do it, but we were actually doing a domino project, so it wasn't too bad. So we're talking about the egg drop problem, and the goal is to see how high can you hold the egg and drop it so that you know exactly where it breaks. And we're going to assume we have 2 eggs. You could, of course, do this with 1 egg, with 3 eggs, etc. There are 2 different things you could try to maximize or minimize. What we're going to try to do first is we're going to try to minimize the worst case scenario. You could also try to minimize the average number of drops needed. And the question would be, would the strategies be very different for that? We talked about doing mixed strategies before. So we talked about some problems where maybe algorithm 1, 99% of the time, say it takes 1 second, and I'll do it a little bit differently this time, and 1% of the time it takes 10,000 seconds. Algorithm 2 maybe always takes 4,000 seconds. So if you can only do a pure strategy in this case, I think we've changed the numbers from we did before, then it is much better to do algorithm 1. But if you can do a mixed, what you can do is you can do algorithm 1 for 1 second, then algorithm 2 if needed. And the advantage is, in this very nice situation, we know that if algorithm 1 hasn't terminated quickly, then it's not going to terminate for another 10,000 seconds. So it'd be much better to switch to algorithm 2 at that point and just forget about all the stuff we're doing with algorithm 1. So sometimes your strategy can adjust based on where you are. So what we're going to do now for the egg drop problem is we're going to go through a couple of approaches. So the first is we're calling it the stupid approach, where you start, well, actually the really dumb approach that was suggested was to drop both eggs at once, which we admitted was too much for a 300 level class. So we started off by dropping an egg from floor 1, then from floor 2, from floor 3, and keep marching up like that. What's interesting is we don't need both eggs in this approach. So this approach definitely seems wasteful. It seems like we should be able to do better than this. And the worst case is if the egg breaks on the very last floor but not before, so it'll take n steps, and on average it'll take about n over 2, maybe plus or minus a half. The next is we're calling it the binary drop. You drop the egg at the midpoint and halves. If it breaks, then you go 1, boom, 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 and you just march up. If it doesn't break, then you drop it halfway between what remains, and you keep marching up. And so in the binary approach, the worst place now is not if the egg breaks at the very last place for the first time, but if it breaks at the halfway point. And so the worst case now is going to be n over 2, and what we're going to try to do now is figure out, on average, how long will this take. All right, so now we're going to actually switch to doing the lecture again. Okay, so since we're doing something like this, there was a suggestion to try to find a recurrence relation. And what we could do is we could do small powers. What do you think would be the nicest value n could take on for us to make this problem particularly nice? Yeah, maybe 2 to the n, right? So, if we want, maybe assume n is 2 to the n. Well, let's do maybe 2 to the k. N equals 2 to the n doesn't sound quite right. All right, so if we have n equals 2, how many drops does it take? It takes 1 drop. We drop it at 1. If it breaks, we know the answer. If it doesn't break, so drop at 1, done.
What if it works at 1? Wouldn't we need to test 2?
So then I guess it depends on as to how we're phrasing the problem. Do we know the egg is going to break from some point? Or do we know that it may break at some point? So if we know that it has to break at some point, we know if it passes at 1, it has to fail at 2.
Or isn't it? Oh, so it won't ever make it to the top floor.
Right. That if it passes every other floor, it has to fail on the top floor. It depends on how you want to phrase the problem. Done.
I guess either way, you can drop it at 2, and if it works.
So we're done if we know breaks, else need 1 more drop. So it really depends on how they give us the problem. It's not going to make a huge difference long term, but do we know that the egg has to break? Okay, now let's assume n equals 4. And what might be actually a little bit annoying is splitting things in half. So maybe it might even be easy if we add a floor 0. Right? So maybe go from 0, 1, 2, because then we're always going to be able to put something right in the middle. So I think that would actually be a little bit easier. All right, so now if we're going to do that, if the first case is if n equals 2, now we have 0, 1, 2. We drop it at here at 1. If it doesn't break, then either we know it breaks at 2 because we're assuming it, or we drop it at 2. And if it breaks here, then we drop it at 0. So if let's assume we don't know the egg has to break. So if egg doesn't have to break, drop twice. Now let's do n equals 4. So we have 0, 1, 2, 3, 4. We drop it at 2. If it doesn't break, so case 1, no crack. How many drops does it take now?
Now we can drop at 1.
Right.
Do we know that it has to work at 0?
No, we don't.
Or if it doesn't crack, it go up. Sorry.
This is where things sadly get annoying, because it doesn't fit perfectly. The powers of 2 doesn't fit perfectly. So no matter how we're doing it, we're getting stuck. Right? Which is quite annoying. You'd like to drop it and go back to the case of 2, but for 2, we're trying to do it with 3 people like that. So here, how many more drops is it going to take for the worst case? It'll take 2 for the worst case. On average,
I think doing small cases is kind of messing us up.
or should we do really small cases and not try powers of 2?
So I think when
Or you want to do something big?
yeah.
Okay.
When you do really small cases, you get like
Okay.
x in the way.
Okay, so let's try a really big case. Let's go from 1 to n, and we drop it at n over 2. So if crack at n over 2, then on average it's going to take n over 4 drops. So on average, n over 4 drops. And worst case, n over 2. I mean, maybe we're off by 1, but this is ballpark. And now, let's assume it doesn't drop. It doesn't crack. So if no crack at n over 2, now what we want to do is we want to put in whatever the average value was. So on average,
I think this is
we
where
want to set up a recursion.
right, but the thing is like it's like f of n equals
What if we do something like this? On average, it'll take a of n over 2 drops.
right.
And then worst case, it'll take w of n over 2. And now the formula we would get is the average with n drops. So half the time, it's going to be n over 4. Right?
Yeah.
And then half the time, it's going to be a of n over 2. And then the worst case of n is half the time it's going to be n over 2, and half the time it's going to be...
Well, wouldn't it just be the greater number of both of those? Wouldn't worst case just be n over 2 or
Oh, wait a minute.
n over 2
Wait a minute.
plus 1?
I was going to say plus 1 over here, the worst case of this one.
Then why are you adding
Oh.
them together?
Oh, you're right, you're right. You're right. It's going to be the maximum.
Worst case be
Well, the worst case seems like...
1, because you have to.
Yeah, I mean, actually, the worst case should be... We might even be able to figure out what the worst case is.
Isn't it just n over 2?
It might just be n over 2.
Because it will only happen.
Right, because if the next one doesn't crack, then we've already eliminated a huge number of things. And if it does crack, now, well, we now know it's between those and it's going to be shorter. So maybe the worst case, maybe we can actually just get that this is just going to be essentially n over 2.
For the average, doesn't, so can you say that?
And then for this, I think we have to add 1. So on how long it takes on average, if we have n half the time, it's going to crack here, and then we have to march down, and that'll take basically n over 4. And then half the time it won't, and then we're doing that. And we have to add 1 because we've already done a drop. And then we've got to be careful, do we have to add a 1 here, or I think that 1 is included in the average. We've got to be careful as to, if we're starting at 1 or 0. So there might be a slight tweak here. So then the question is, can we now use this? So we now have a n halves should be 1/2 n halves over 4 plus 1/2 a n over 4 plus 1. And then a n fourths should equal 1/2 n fourths over 4 plus 1/2 a n eighths plus 1, and so on and so on. I'm sorry, yes. And so we should have to do this roughly the log of n base 2 times. So, if the plus 1s weren't here, just as a quick and dirty estimate, so we would have n over 8, then we would have a 1/2, 1/2. So let's write this out. So it would be an would be n over 8 plus 1/2, and then we'll have a n halves, which will be n sixteenths. And then we have a 1/2, and a 1/2 will become a 1/4, and then the n over 4 will be n over 32 plus, now we'll have, I think, a 1/8, and we'll have a n over 64, I think. So we can see it's a really nice geometric series. So we increased this by a factor of 2. So it looks like we're going up by a factor of 4 every single time. So again, this is as a ballpark estimate. Maybe we should get, it'll be n eighths over 1 minus 1/4 roughly, which would be 3/4. So maybe n over 6.
And if you want to add the 1 back in, you would probably get something on the
Order of log n, because those ones are going to be multiplied by small factors.
Yeah.
So on average, plus big O, maybe like log of n. And actually, in fact, it's probably big O of 1 because they've got all multiplicative factors in front of it. So I think we should be fine. So this is a great improvement on the average case, going from n halves to n sixths.
Do you think there'd be a better pivot
Instead of,
instead of n over 2,
yes.
n over 3 or something?
I think there's a much better pivot. So what I want to do about this is I want to show the idea I had. I do not know if this is the best idea. I have not looked. I do have a suggestion from somebody from Swarthmore. I have not looked at what they've done yet. But it all comes down to trying to decide where you want to do that first drop.
I was thinking of starting at 10 and then going to 20 and then going
Good. Why 10?
because you have 2 eggs and it's the square root.
Yeah, that's what I want to do, is I want to drop at the square root. Because we have two competing influences. The first is the smaller drop we do, the more drops we have to do before we probably find the first fracture. But if it fractures, the smaller region we need to search. So we have two competing factors going on here, two competing tugs. Over here, the n over 2 is great if it doesn't shatter, because now we've eliminated a huge number of things. But if it shatters, we're now up the creek. So what if we instead drop it at the square root of n? And you could potentially do a little bit better, maybe put in some kind of constant times the square root of n and try to optimize. What I want to do is I want to try to argue a little bit more generally. I also agree, my gut is telling me do it at the square root of n. What we could do is say drop at n to the delta. We won't worry about a constant in front right now. And then try to see what is the best delta to use. So this is something I've learned in analysis classes. Give yourself a free parameter. Don't force yourself to make a decision too early on.
I did some analysis,
Okay?
and it was basically if you don't have to worry about the number of drops, if you can say, with the same number of drops of the first egg,
Right.
I'm going to find out that tens.
Right.
I'm going to find out basically with the first drop.
You'll get the tens digit?
Well, that was what I was thinking when I knew the answer, but just kind of like some fraction.
Right.
And then with the second drop, I'll get another fraction, and then the expected value is going to be, the number of times I have to do the first drop plus the number of times I have to do the second drop, and some, times some constant.
Right.
So it's basically just, two numbers multiplied to 100.
Right.
And minimize their sum. What makes it slightly more complicated is when you drop at 10 and it breaks, you do less drops than when you drop at 90. So I was thinking then maybe some sort of start by dropping at 12 and then start by dropping at 21.
Right. And so what that could be is some kind of dynamic adjustment. And that maybe the first drop is a little bit higher, but we're doing maybe a certain fraction. Maybe we're not doing square root. That's why I might want to put a constant c. Maybe it's like root 2 square root of n or something like that. And you're basically doing like root 2 times the square root of the length that you're doing, so that the first one is not equal. And that's because precisely if the first couple of drops are all good and then you have one deep down that's bad later on, you have a huge cost to pay. So you want to search a little bit farther on the first. So I think what you just said is that dropping at the square root of n is not going to be optimal. But it might be close. Maybe it could be off by some kind of multiplicative factor. So if we drop at n to the delta, at most n to the 1 minus delta drops before it breaks. And here what we'll do is we'll drop at n to the delta, then 2n to the delta, then 3n to the delta, ... And then once break, now we need at most basically n to the delta drops. Now we have to do, well actually I guess it's n to the delta minus 1 drop. We keep going boom, 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 but we've already used 1 drop maybe. Something like this. I'm not going to care if I'm off a little bit by some constant. So once we drop it, now we know a range of size n to the delta, and we just have to try each single one. So the worst case would be we do something like n to the 1 minus delta drops, and then we add n to the delta.
Why n to the 1 minus delta drops?
Well, it's not until the very last one that we get our first break.
But why would that be n to the 1 minus delta?
Well, how many times do I have to move up in steps of size n to the delta before I get to n? What times n to the delta is n to the 1? The last one over here should be n to the 1 minus delta times n to the delta. And then I finally reach the end. So the worst possibility is I take n to the 1 minus delta. And so this is now a function of delta.
It would probably be n to the 1 minus delta minus 1. You probably don't have to check that.
Right.
Right, like you check
Well, this comes down to, do we know if the egg breaks or not?
Right, but if we check 90, we don't want to check 100. We want to just go
Well, no, but if the egg doesn't have to break, then we do want to check maybe 100. Well, you're right. We probably don't want to check that. So I'm not going to worry about a minus 1. So it should be something like this. And then we want to find out where is the smallest for large n. And the feeling is that you've got two competing influences. As delta gets closer to 0, that makes this large. As delta gets closer to 1, that makes this large. Probably the best thing you can do is delta equals a half. And this is now a calculus problem.
I think you could use an AMGM.
Oh, that would be great to use AMGM. So the arithmetic mean, which is n to the 1 minus delta plus n to the delta over 2, is greater than or equal to the geometric mean, which is going to be n to the 1 minus delta, n to the delta with a square root, which is just square root of n. Wait a minute. Wait, the geometric mean is just multiplying the two together, right? And the arithmetic mean is greater than the geometric mean, but the geometric mean here is always constant, right? I got excited too soon.
So now we know that if delta equals 1/2, it satisfies it's the level.
Good. So we can actually survive like that. So the best we could do is to get this quantity to be roughly of size square root of n. And so taking delta equals 1/2 will get it as small as that. So now, best if delta equals 1/2. So that's going to get us as small as we could. It is also just a nice calculus problem to see what value of delta will make this as small as possible for large values of n. And I'll leave that as a nice calculus exercise. But this gives us the worst case scenario without too much trouble. The best case scenario is going to be roughly of size n to the delta. And then you can ask, on average, how much is it going to be? Well, if delta is going to be 1/2, it's going to be on the order of square root of n. So average case is going to be on the order of square root of n, which is amazing. This is a power savings over what we had before.
And I think if you generalize it to like xx,
Right.
it would be on the order of the x3.
Right, so if we now do 3, would we get it on the order of n to the 1/3?
I think you would, because basically, if n is large enough, the most, like, for the average case, the vast majority of the drops are coming from, once you've broken the first two, and
Right.
you're iterating up.
Correct.
So that you'd be iterating up on the order of n to the 1/3.
Right. So for class for is this Wednesday? Yeah. Okay, for class for Friday, think about what you would do if you have 3 eggs, and then in general, what would you do if you had k eggs? And I think you would want to do some kind of big power step for the first, and then what you would be left with would be an interval of size n to whatever power you have. And we know the best we can do is square root there. And so now you would have an attempt to try to just do this formally. But what I like about this is a much better answer than the order n algorithms we're getting. The domino tile problem, the domino stacking problem we're doing, has a similar wonderful solution. The best approach you see in Calc 3 is on the order of log n. In terms of if I give you n dominoes, so for those of you who didn't see all the technical malfunctions, the question is, what's the best way to hang dominoes on top of each other so that they support each other? When you go like this, the best you can do is about log n. So the first domino, you want to have the weight supported. You move the next one over 1/2. The next one moves over 1/3, then 1/4. And if you do this properly, it will survive. And you get the harmonic series. So that gets you a hang of on the order log n. I think the world record, one of the people involved was my math professor freshman year, is you can actually get a power of n. Not log n, you can get a power of n with n dominoes. And so we will talk about that on Friday after we continue with the egg draw problem. The whole point of all these things right now is to just try to hammer home how easy it is to be making assumptions about problems. That when we're building with these dominoes, were you building with the dominoes in a certain way? And then eventually did you realize I can play with them differently? That's the whole point. It's very easy to have these assumptions and not to be aware that you're doing it. So if I can get you at least one point in your life when you're doing research, when you're doing something in finance, to realize you're making an assumption, this is a successful class for me. That's my goal. Once in your life for you to realize when you would not have realized otherwise. All right. If people want to take some dominoes home with them to play with them, absolutely, perfectly fine. All right, just let me know, and then think about this problem for next time. Okay.